Hello students, welcome to lecture number 9. In this lecture we are going to discuss the line spectrum of hydrogen. This is K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Here we know that spectrum is a very important document when we want to know the internal structure of the atoms. It is a very important information we can have from this line spectrogram. So how the line spectrogram is produced, that we can now understand. When we pass electric discharge through the hydrogen gas in a discharge tube in a very low pressure, there is a decomposition of the hydrogen molecule into the energetic hydrogen atom, and this energetic hydrogen atom produces the radiations of different wavelength, and when it is passed through a glass prism and it is captured in a photographic film, we will get a different types of lines with a different series. So you can see from this schematic diagram, it is a discharge tube. Here you have the hydrogen gas, and this hydrogen gas has been passed with this electric discharge, and when this electric discharge passed on this hydrogen gas, you will find that there is a dissociation of the hydrogen molecules into the hydrogen atom, and this hydrogen atom is very much energetic, and this will going to create a radiation, and when this radiation is passed through a glass prism, this is a glass prism, and it will be received in a photographic film, and we will get a spectrum, line spectrum, and this is called the hydrogen line spectrum. Closely analyze this, you will find this type of series of lines. So this is a photographic plate, and you see there is a different series of lines. In the first, that is, we see this is the Lemon series. Here the line appearing on the photographic film, that is on the UV range. The wavelength of this line that is appear in the photographic film, it is having the UV range, and this is called the lemon, because this name of the series is given after the discoverer who has discovered this line. This name has given after him. Then we will find that is another important series. This is called the Balmer series. And here the wavelength of the line is found matches with the visible range. Then we will have another series that is called the passive series. Passive series, and it is having the wavelength is infrared rate, IR range, infrared. Then is another series that is the bracket. Then there is another series, and it is also the infrared. Then you have the profound series. Then lastly there is a series, this is called Humphreys series, and it is far infrared. So this type of series you will find in the photographic plate of the hydrogen atom. Hydrogen atom is going to create the emission spectra that we have discussed in our previous video, the video number 8, that what is emission spectra, because these are going to be emitted bright lines in the spectrogram, and that corresponding to the different wavelength. So this is how this is called the light spectrum of hydrogen. To discuss how these different type of lines having the different wavelength has been produced. First, that is Lyman series, when the electrons from the higher level that will come to the first level, and it will be 2, 3, 4 this, and it will produce the ultraviolet range. The range of this series of this light is the ultraviolet, and here the electron has been jumped back to the number 1 level. Second series, that is the Balmer series. Here the electron is dropped to the second level of energy, that is N equal to 2, and here you can find the visible range. Then you have the passive series. Passive series you will find this is infinity R. Then you found the bracket series. Then you found the profound series. And then Humphreys series. Humphreys series, this is far infrared. So this type of series of lines have been produced in the line spectrum of the hydrogen, and that is basically you can found that the level is the first one level is remain fixed. Here the first level, the electron when jumps back to this level, that will be fixed for a particular series. For the Lyman it will be n equal to 1. For the Balmer it is 2, the passage is 3, and bracket it is 4 and 5 and 6. So you have to remember, for the Lehman series, the electron from anywhere of this energy level will be fall back to the n equal to 1. For the Balmer series, that will be n equal to 2. For passage series, that will be n equal to 3. So that you have to always remember. And with this falling, it will always going to give a different level of radiations having that different energy and wavelength. That is why you can see here the energy gap is very high. In case of Lehman series, energy gap is very high, and that is why you can see it is having the higher frequency. The radiation will be higher frequency, because we know difference of the energy. If the difference of the energy between the level is higher, then the radiation will have the higher frequency, and the wavelength will be inversely proportional to this energy. In case of visible range, you also found that it is lower than this, the frequency is lower than this ultraviolet range, then it is infrared, then the 3. For the passive bracketed found, you will find the infrared series, and it is Hampe, that is your Hampe series. So this is, now we want to calculate the frequency wavelength of these lines, and that has been given by a very important formula given by Rydberg. Rydberg was a spectroscopy, Sweden spectroscopy. He has given a formula relation with the wave number. This is wave number, and it is wave number is inverse of the wavelength, and that is given by RH into 1 by n1 square minus 1 by n2 square. Here n1 n2 is always greater than n1. That will be there. Now, from this formula is very much helpful for the numerical purpose. You will do some numerical, you will understand how important this formula is. Here this is Rydberg constant, RH is Rydberg constant, and this has the value, this is Rydberg constant. You have to remember this constant. Okay, this is very important. So if you want to find out the wavelength of this line in the spectrogram, line spectrogram of hydrogen, you have this formula. But for the hydrogen-like species is, suppose this is He plus or Li2 plus, B3 plus. These are this hydrogen-like species. Why it is called? Because hydrogen have the 1 electron in their orbit, and this helium plus will be 1 electron, lithium plus 2 will be a 1 electron, and beryllium 3 plus will be the 1 electron in their orbits. And for those, suppose you have been told calculate the frequency of this hydrogen-like species, then if you apply this formula, it will be incorrect. This formula is only applicable for hydrogen. But for this, you have this formula, you have to always remember, that is here only addition in this formula is the atomic number square. Here it is given the atomic number square. So this is the things for this line spectrum of the hydrogens. Now there is something that we want to discuss in detail, this type sometime questions in this regard may arise, that I will discuss now. Question arises for a particular series. Suppose it is 11 series. In this series, all the lines appear in the spectrogram, appear in the spectrum. Whether this intensity will be same or not. The answer to this question, the intensity of the lines will not same. So if not same, so what will be the determining factor? Determining factor is this. Suppose for the Lemon series, when the line produced, because every transaction when we are there is a n2 to n1, there is a one line is produced, n3 to n1, one line is produced. Like this way, for a lemon series, when there is the transition from n2 to n1, the intensity of the line, city of line shall be higher than the line N3 to N1. When this transaction, the line produced by this transaction N2 to N1, the intensity of this will be higher than the N3 to N1. That you have to always remember. Number 2, the number of lines. Number of lines, that is also depend on the difference between the energy level. The number of lines, suppose as for example, in the 11 series, there is a transaction N4 to N1. The number of lines will be, that will be summation of this difference, that is N4 minus N1, that is, we can write 4 minus 1, that is 3, summation of 3, 3 plus 2 plus 1, that will be the 6. Means when the electron drops from the N4 to N1, there will be the 6 lines. In this way, you can calculate for the N3 to N1, N2 to N1. For N3 to N1, what will be this? And it will be accordingly, you have to calculate. So this is how you can see the intensity of lines and the number of lines has been monitored by the difference of the levels of the energy from where the electron has been transferred. To make the concept clear, in this line spectra of hydrogen, we will do some numericals. If the shortest wavelength of the hydrogen atom in 11 series is X, then the longest in the passage series is H plus. In the H plus 1, this is the hydrogen-like species that we have discussed before, is option is here given. Now we have to see what do we mean by the shortest wavelength and what do we mean by the longest wavelength. When the shortest wavelength going to produce, when the longest wavelength going to produce. Shortest wavelength means when the radiation at the highest energy. The radiation of the highest energy at that time when the electron is fall from the infinity to these lamencies matlab n equal to 1. So at that time you have the shortest wavelength. Already we know there is a formula, that is Rydberg formula, that is 1 by lambda is equal to Rydberg constant into 1 by n1 square. This formula we already discussed. Now when there is a shortest wavelength, means here n2 will be infinity and n1 is 1, because it is the Lyman series. For the Lyman series you will have the n1 is always 1. So from this we will able to calculate that. Now as a condition it is giving the shortest wavelength is x, then we can equate it 1 by x is equal to RH, and 1 by this will be 1 by 1 by infinity, that is 0, it will come in around this. So we get this RH equal to 1 by x. Now the longest wavelength, longest in the passage series, means longest wavelength, is talking about the longest wavelength. Longest wavelength will be when passage series, we know that when n equal to 3. N equal to 3 means initial, that is where the electron will fall back. For the passage series, electron will fall back in the n equal to 3 from where it will be n equal to 4. For Balmer it will be n equal to 2. So for passage series, when the longest wavelength will be in the h plus 1. Another thing is given, this formula we have to modify here. This formula will be 1 by lambda equal to this formula z square RH plus 1 by n1 square by 1 by n2 square, because this formula is applicable for the hydrogen atom, this formula is applicable for the hydrogen like species. So this is Z for the helium. For the helium, Z equal to your 2, so it will be 4 into RH. So for the passage series, N1 equal to 3, means it will be 9, N2 will be 4, because 4 to 3 it will have the longest wavelength. So this will be 1 by 16. So we get this value 4 into RH, that will be coming around 7 divided by 9 into 16 means 4. So when we equate this, we will get this figure 36 into x by 7. So when shortest wavelength in the Lyman series is x, this longest in the passage series in h plus 1 will be 36x by 7. Okay, this type of question will ask, and if you have the clear cut idea, then you can able to easily answer it. Okay, I think you understand this, how I'll solve this. Again, this type of question that may be asked, the frequency of one line in the passage series of hydrogen atom is this. This is Hertz. The quantum number into which produce these transactions, that we have to see. Option is given here. To apply this formula that we have already discussed, that is 1 by lambda is Rydberg constant into 1 minus n1 square by 1 by n2 square. Now we can modify this formula, because we know that lambda is equal to C by mu, we know. Okay, so if we put this value here, so it will be mu by C is equal to RH 1 by n1 square minus 1 by n2 square. So frequency it is has been given. C is the speed of the light. RH we know that is 109677 centimeter this. Okay, so we can easily calculate, and passages is n2 is equal to 3. So when we put all the value and it will give the answer, you will calculate yourself, that this will be given 5. So when quantum number n equal to 5, then you will get this frequency of the line. One line having this frequency you will get. So from this discussion, one thing we can conclude, that the line spectra is a very important aspect of the atom, and it is the unique. And number 2, as we go for the line spectra for the other atoms which having the number of electrons is more than 1, that is much more complex than the line spectrum of the hydrogen, but there is always you find a regularity, and this question we will answer in the next video when we are going to discuss the Bohr models, Niels Bohr's model, when he improved the model of the Rutherfords. Okay, and that is all for the today's video. I hope you understood everything, each and every point. If you do not understand anything, then you can comment on the section box so that I can able to give you reply, and then